Well, looks like we can start. Welcome back, folks. For today's class, we're going to run through the section notes, section 2.2. And if we have available time, we'll be running through section 2.3. Hopefully we get more people in today for only the second day, kind of light on the class, but if it's going to be a small class, then we'll make the most of it. No worries. Any questions at all, folks, to get us started today? Okay, well, running through section 2.2, there's a lot of stuff in there. There's a pretty big section. Really, it's a big overall review to get us all on the same page so that we're well prepared when we go into the further sections like 2.3, which is published down here. So the major objects that we discovered, or discussed rather, were the floor function, rounding down is essentially a way to think about that, and the ceiling function, rounding up. Next, we're going to look into a couple things with properties of exponents, logarithms. It might be kind of a slow and boring rehash once again, but it's always good to take a second look at that kind of material. Then we'll look into modular arithmetic, which will be probably something new for quite a lot of people. Well, any questions at all, folks, before we get started today? Okay, let's give this a try. So back to the section notes, or maybe just a couple announcements for reminders of how things work in this course. If you did click on this, section 2.2, you'll notice it's been annotated a whole bunch. These are just all the things that we wrote down on the last class. If you notice that something could have been an error there, don't hesitate to let me know. I'll go back and correct the record. The error on YouTube is forever, but that's no big deal. Mistakes do happen. But if you do need the blade collection note, maybe you're going to print out a second copy, download a copy to your computer, go to this folder right here, and these get published on a section by section basis as we get more and more notes on the Moodle website. If I have to make a revision to any of the notes, I'll always try to revise it here as well, so all the files are in parallel in that kind of way. Well, I think that's really my only major announcements for today. This is a pretty traditional course. The online textbook is freely available. So I think especially in the land of the ISU book bundle, this is probably one of the easier courses to get going and clearly get started in. Well, let's jump back into example 3 that looks like where we're at. And it looks like lots of definitions, but again, think of this as just a review kind of work where we're just practicing more and more about exponent laws just so that we have them under our belt. I'm not going to ask a lot of examples like this. I think there's just a couple of these in the homework set. But the emphasis on solving this one is not so much to put it in the calculator. I mean, we can, there's no harm. We can just go, we need a good numerical value of 16 power 2/3. There it is, 6.349. And that's a perfectly great result depending on what you're doing. But really the purpose of this problem is to practice all of this stuff, which is still very, very important. So let's give it a try. There's a lot of different kinds of answers to this. So when you do yours in your homework, you might have your answer formatted a little bit differently than a fellow student, and that's okay. All we're really trying to do is simplify this as much as possible. In fact, I don't really like the way I wrote out the verbiage on this. Instead of saying evaluate, that's like saying get a numerical value. I think it's better to say on this one, simplify. Because that's more in spirit of what we're actually doing to this thing. So let's start off on the far left, 16 to the power of 2/3. Loads of things you can do to try to simplify this. Again, there's lots of approaches, but starting with definition 2.6, the big feature about this problem is we have a fractional exponent. So if we wanted to, we could break it down in this kind of way. So this 16 to the power of 2/3, oh, I can't draw well, that's highlighted, is equal to 16 to the power of, let's go perhaps 1/3 to the power 2. So this would be a decent approach if you decide to go this route. But using this formula specifically, it just depends on the problem. Sometimes it is a great approach. Down here, it looks like this is not getting us too far, really. We can simplify 16 to the power of 1/3. Let's go take a different approach. So I'm going to leave this here, and let's say second try. You can also do something like 16 power 2/3, and re-express this in the way, in a certain sense, as 16 power 2/3. I didn't really do anything too earth-shattering there, but I wrote the parentheses in because I want to change the 16 to something else that's better for us to deal with. Let's write in 2 power 4. So we've got prime factorization. That's being raised to the power 2/3. And now these exponents here, we could follow exactly what's said in this definition, 2.6, or we can break this down by taking 2 to the power of 8 to the power of 1/3. All I've done on this step is squared this power 2 power 4, which means 2 multiplied the exponent, we're up to power 8, leaving the cube root to power 1/3 behind, which is a true cube root, since anything like of this form is referred to as an nth root. Any questions, folks, to that stage? Okay, so this is the point where there's lots of ways to simplify this. I think for me personally, if I was dealing with this, I would leave the power 1/3 here. Oftentimes that's more helpful than not. I think if you prefer to write it in as a cube root, no harm done either. But your 2 power of 8, notice how that might interact with 1/3. We're going to use an exponent law that goes like this, right over here. And so if we arrange things just right, and also use this exponent law, we'll get a good simplification. So let's take that 2 power of 8 and write it 2 to the power of 6 times 2 to the power of 2. So what I've done there is use that exponent law going in reverse, or excuse me, going in the forward direction rather. The power is still 1/3. And now this exponent law, let's see here, this one says that 1/3, which is playing the role of x, can now distribute inside. So we get 2 to the power of 6 to power 1/3 times 2 to the power of 2 power 1/3. This is the irrational part. You can't do anything with that, simplifying it down to some integer. This is an expression we're going to leave pretty much in that form. But this portion right here is the exact part. This is an integer. The power 1/3 and the power 6 can interact. This is really just 2 to the power of 6/3. So we get 2 to the power of 2. Now multiplying this expression, the power 2 on the inside, power 1/3, can also interact. We get 2 power 2/3. Honestly, it feels like we're right back where we started, but it's a true simplification because now instead of 16's power 2/3, we have isolated this down to the irrational portion and the integer part, 2 power 2. So we get altogether 4 times 2 to the power of 2/3, if you decide to simplify it in that route. Again, there's even more stuff you could do with this if you kept on going, or it has the same base as 2 if you prime factor this, and then you can combine the bases and just keep on going and going a little bit further. But if you find that this feels like a natural stopping point on the homework set, then I'd say stop right at that step, and you're in good shape. So this example here, again, is kind of a weird one for this class, but its whole purpose is to get us more familiar with these kinds of exponent laws. Any questions, folks, with the rundown on that one? Okay, probably the better reason why we're discussing all these exponent laws is not as much for the review. I think a lot of people are highly familiar with this kind of content, but it's more because you're dealing with an exponential function. That's just inverse to the logarithmic function. I think for a lot of people, these are the concepts that are a little bit more vague. So let's spend a little bit more time on this and work through these kinds of results. So if we're dealing with a logarithmic function, it's a full functional inverse. But one thing we do require is your base of the logarithm cannot be 1. That's because the base of an exponential function cannot be 1 either. And it must be greater than 0. So a positive real number for the base. Oh, it says it right here. Positive real number for the base not equal to 1. And here we're picking out a positive value for x to express log base b of x. This is the number that you have to raise the base b to in order to get the input x to result. Or better said another way, you have something written down in logarithmic form, you can just retranslate that to the same exact information expressed as an exponential equation. And notice what happens with that. We have the base of the logarithm being the same as the base of the exponential function. one humongous punchline to inverse functions is that your input x and your output y get reversed. This is exactly what we're seeing here, since in the exponential form, that's the input y, but down here, that's the output. So we must switch input to output, and same with this x to this x. So that's the big idea of dealing with logarithms. If you're familiar with doing these two conversions, then evaluations are really pretty rapid. And just for the sake of completeness, these are the logarithmic properties that are used quite often. I would say these examples rather are just more about practicing dealing with logarithms. And the first one is kind of vague. It's open to interpretation. If you saw log 32, it's highly dependent on context. In statistics, it has a particular base, usually base 10. In mathematics, we really usually write ln, but in some books, log is meant to be the natural log, base c, mathematics. Anyone happen to know what this ought to be in a context of applied discrete structures, potentially? It would be base 2, absolutely, because the major concepts and applications that we're going towards is computer science. And in computer science, the convention is log x is meant to be log base 2 of x. So if this is log 32, we interpret this thing to be log base 2 of 32. And from here, it's all up to how familiar you are with logarithms. Anyone happen to know the value of this one?
Is it 5?
It would be 5. Good call on that one. So if you just know it's 5, I'm going to accept that definitely for full credit. And even though it says evaluate by hand showing all steps, well, if you know the value, you're done. There's nothing more to do on that thing. But just for the sake of showing those steps, here's one way to think about this if it didn't jump out at you right away. So go log 32. Same step as before, go log base 2 of 32. And we can make this a logarithmic form. It has to be an equation, so just go equals y. Convert it up here to exponential form. We would have 2, which is the base. The y here becomes the exponent on the base. The input to the logarithm becomes the output to the exponential function. And now we're just trying to solve an exponential equation. Usually these are a little bit easier to solve. If there's an exact value here, this is an easier equation to solve. We can write this as 2 power y equals 2 to the power of 5. And at this stage, we know that the log base 2 of 32 has to be 5, because the definition of a logarithm is this 5 here as an output is the exponent that you have to place on 2 in order to get the output 32. So that's our rundown of logarithms. Below, I just have a couple more tricky examples. But any questions at all, folks, with the evaluation there? Okay, let's try it again. Pretty riveting stuff. So another one, log base 3 of 1/81. This one's a little bit trickier, but it's still kind of like this if you think about it right. Any volunteers for an output on this one? Yep. Sorry, say again? Absolutely, good call on this one. This will be -4, and the same kind of approach would reveal that if we're not too sure. Let's write that out just for a quick sketch once again. So take log base 3 of 1/81. You can call that output y. Then from here, drop down to a new line where we have the base 3. Y goes over, so it's 3 power y. The input comes down over here, but let's start maneuvering with that input. You could call this 1/3 to the power 4. Then, using properties of negative exponents, this becomes 3 power y equals 3 power -4. And now we have a solution. If the bases are the same, then the exponents must be equal, is the concept being used here. So we have a matchup on this one. Let's try this one more time, but any questions first, folks, with either the sketch on the right or the exact value on the left? Let's try it one more time. The natural logarithm of -4. That one's weird, just a heads up on this one. Any knee-jerk reactions folks have to this? What would you say if you saw that on paper? What's the best way to express an answer on this one? It's truly a tricky question because it depends on the set of numbers you're dealing in. If you've taken a lot of complex analysis dealing with complex numbers, square root of -1, that actually has an answer. You can evaluate that, but you have to extend beyond the real number system. If we're in the real number system, anything with a negative value on any logarithm to any base whatsoever is purely just undefined. Let's say undefined due to that negative right here. But if we attempted to evaluate it using the same processes over here, we should know what goes wrong. Why can't we define it if we're just purely in the real number system? So let's make that approach again. So the problem started off with natural logarithm -4. That's just saying take the log of the base e, Euler's number, of -4. We can convert this now to a logarithmic equation with an output y, and same approach as before. Take e power y. This will be equal to -4. Well, you might be thinking of, well, how in the world are we going to make -4 have base e? But that's totally an unrelated problem to us now at this stage, because we have a related result here. This automatically has no solution. And the reason for that is, if you think about visualizing the graph of e to the x, it looks like this. It has a horizontal asymptote, the x-axis, y equals 0, intersects right at 1, and its graph goes about like that. Y equals e to the power of x. The amazing thing about this graph, which is kind of hard to convey, is it will never even touch the x-axis whatsoever. So in other words, e to the power of a is bigger than 0 for all a in the real number system R. So the no solution here is the whole reason this expression is just undefined. We typically wouldn't even put equals right here because that would say that this is a real expression. It's just pixels on the computer system now. It has no corresponding concept as a mathematical object. Unless, again, we extend to the complex number system. But any last questions, folks, with just that quick rundown on logarithms? Okay, well, that's our quick rundown on dealing with exponents, logarithmic expressions as well. And I think this is probably the more exciting part of the notes, dealing with modulus arithmetic. So I find this concept to be really slippery. It's not too bad at first until you make one weird change on the integer n that you're dealing with. So a lot of ways people think about modular arithmetic is if you take a number and write out, oh, where's my expression, n mod k, what you get as a result for that is simply the remainder when we divide the integer n by k. Amazingly, though, you can combine our floor function that we dealt with last class meeting and re-express this as n mod k as n minus k times the floor of the division by n over k. This sometimes feels like it's unnecessarily complicated, because if you look at 17 mod 5, that's meant to be the remainder after you divide 17 by 5. That ought to be a 2, right? 5 by 3 gives us 15, and then there's just a remainder 2 left over. So if you did this problem on homework set and you just said equals 2, I would say that's totally fine. I would assume that you're probably looking at this portion of the definition for the modulus. But let's try this again, just to get a good feel for this, because it truly is a really important formula. I mean, one practical side is if you had to code this up, you don't necessarily want to code up an expression like that without some neat trick. And this is a really efficient, neat trick to get modulus implemented. But there's a bigger problem. The reason why we really like this formula is this integer n can be positive or negative. And when it's negative, the idea here that's been expressed, even by our author, starts to get pretty vague as he admits himself. So there's another way to think about these things. Let's practice the formula, and we will do something with a negative one and get a feel for what is that even trying to express. So here's our practice with modulus. If we want to do 17 mod 5, if you know the answer and you just say 2, that's good enough for me. Let's do it as scratch work on the right here. 17 mod 5 can also be rewritten as we start with the value here. That's going to be 17 in this case. Subtract the value here, what you're modding by, this is by 5, multiply it by the floor of 17 fifths. At this point, I'd probably just grab a quick calculator. Let's take the 17 fifths and get a decimal value. So we have 3.4. I probably should have known that, but let's just go with that nice exact result. 17 minus 5 times the floor of 3.4. If you think about doing long division step by step, this kind of starts to make sense on why the floor function is coming into play here to give you your remainder. So we'll have 17 minus 5 times. This was the concept from last class. Any volunteers for the floor of 3.4?
It'd be 3.
Yep, good call. Thanks, Mike. So this will come out as 3. That means we have 17 minus 15, and we get a value of 2. What people would expect here, if you divide 17 by 5, we expect a 2, and it is truly the remainder. It's kind of neat to see that this formula just works just fine if you decide to go that route. How about for this one? Let's use the formula on this, just again to see how it works. But any volunteers for what would be 5 mod 17? Exactly. 17 does not go into 5 whatsoever, so 5 is automatically the remainder. If this was 6, the result would have been 6. If it was 16, the result would have been 16. But if you put 17 right in front of that, the result is 0, no remainder. So these values are going to go from 0, 1, 2, 3 up to 16, and then just start repeating over and over again. We have kind of a cyclical type of arithmetic going on with this. But let's see if this really pans out. We're expecting a 5 from the result. Let's hit it with this formula up here. I'm going to write this one in black to say I'm going for this as the official answer on this one. Take 5 minus 17 multiplied by the floor of 5/17. We'll get 5 minus 17 multiplied by the floor of, let's take a look at that one. 5/17 comes out as about 2.94. Excuse me, 0.294. But that means the floor of this one is just going to be a 0 altogether. We get 5 minus 17 times 0, which gives us a result of 5 altogether, which is what we were expecting here. Any questions, folks, with that value so far? Okay, and maybe just a really quick concept on this one. We can also say here that n mod k equals n for all n equals, let's go 0, 1, 2, all the way up to k minus 1. So that's the concept we were looking at here. As soon as we knew the thing we're dividing by, 17, exceeded 5, the answer was just 5 altogether. Think of this as us just practicing the formula. Now here's the weird one. Everything we did here really is the remainder after dividing by whatever the divisor is. 5 in this one, 17 in this one. Here it becomes a little bit vague. The remainder would be 3 if we're thinking about dividing by positive 13. If we multiply our whole answer by the result of -1, we might think of a remainder as -3. Neither one of those is the answer to this question here, -13 mod 5. This is where the formula really, really shines. And it's also where this interpretation breaks down, sadly. So we'll give a new interpretation which works for negatives as well as the other values all at the same time. Okay, so here's our next approach. Any questions or comments so far before we try out part C? Okay, as before, we'll just write this out as it's going to be negative 13 minus 5 times the floor of negative 13 fifths. Notice what I did have to do here is, if we have the value of negative in front of the mod function, the negative will also convey to this location as well as the starting location. So now we need negative 13 fifths. We get a value of negative 2.6. So this is negative 13 minus 5 times the floor of negative 2.6. I recall last class meeting, this one was a tricky one for me, at least. I believe this one ought to be a negative 3, but just for extra visualization on the floor of that, let's go negative 3, negative 2, negative 1. The negative 2.6, here was my critical mistake in last class. We've got to put it on the right spot on the real number line if you use this approach to analyze it. Here, we round down to the next nearest integer, so the whole value will be negative 3 in this expression. So now we've got negative 13 minus 5 by negative 3, so this turns into negative 13 plus 15. So now we know negative 13 mod 5 is positive 2. Our really big struggle with this one is to say, what does this have to do with division? It's a pretty big stretch, I'd say. A better way to think about this is multiples. When you're dealing with something mod 5, your output you're getting is the distance to the nearest multiple of 5. It's one thing to say it, but it's much easier to understand that by just drawing it out. So let's do that right away. So here's our real number line. We began at negative 13 with the inputs right here, but we're mostly interested in the multiples of 5. So the nearest multiple to the left is negative 15. Nearest multiple to the right is negative 10. And this value 2 here is no coincidence that it is the distance to the nearest multiple of 5 that the integer here, negative 13, was next to. Let's see if we can get a really quick statement here. The value 2 is the distance to a closest multiple. Let's say this with a definite article. I think that just flows better. There's only one, to the closest multiple of 5, going either in the positive direction, but in this time we had to go into the negative direction. So that's another way to think about what modulus is trying to do. Negative values make the interpretation a little bit vague, but it's really the same kind of interpretation we could apply to the other values as well. Well, any questions at all, folks, at the moment? Okay, and just for the fun of it, here's one more. Here we have nested mod functions. Parentheses and order of operations are the typical things we would do. Even though it's strange arithmetic from before, same kind of rules apply. So first thing we've got to do is 20 mod 7. We can use the mod function discussed right here to solve this one, but we're feeling confident on what mod should do if we have positive input on the left. Shouldn't be so bad. So let's see if we can run through this one just by kind of following our nose. 20 mod 7. Well, 2 by 7 is 14, 2 by 3 is 21. So this goes in, 7 goes into 20 twice with the remainder of 6 altogether. So now we're looking at 6 mod 3. So if you have nested mods, that's pretty much all we do, work inside out. Last thing we need to do is find the value of 6 mod 3. Anyone would spot what it is just by visual inspection.
That's a really nice, convenient one. It's 0.
Yeah, absolutely. Some people are indicated this way in class. Thanks for your response as well. If you notice that the value on the left is a multiple of the value on the right automatically 0? Or another way to think about it, 3 goes into 6 twice with a remainder of 0. So that's what the mod function is all about. There's a lot of really interesting connections to this function to abstract algebra in an interesting sense. So the mod function creates an algebraic structure studied in modern algebra, called things along the lines of groups of symmetries. So this is a innocuous looking little function, but it has a lot of interesting, very deep connections to abstract algebra, as well as computer science. Kind of a simple idea, the remainder after division, or the closest distance to a multiple of 5. Well, after dealing with the modulus function, this is pretty much close to the wrap up of this section. The last concept I had on here was just dealing with summation notation. The reading on summation notation is pretty intense. So I did write down on the notes here for the reading, read pages 6 through 17, read pages 20 through 22, only because I felt like some of the stuff that we were doing in this section on summation notation, product notation, goes a little bit beyond what we would truly need. So in this section, we're only targeting the reading to just familiarity with sigma notation, summations. So if you've taken Calculus 1, Calculus 2, you've probably seen these a lot. If we put a limit in front of this and take the limit as n goes to infinity, we call this a Riemann sum. If you haven't taken calculus, no worries. That kind of stuff's coming down the line later on. And just knowing this is super important and helpful for calculus. One of my frustrations with teaching classes like calculus or linear algebra is that these base concepts, especially set theory, doesn't necessarily get a really great treatment. We're just expected to know it going in. That's pretty tough in my opinion. But here's what's going on with the good old summation, or sometimes called sigma notation. We take a set of numbers, a sequence of numbers, write down a summation in this sort of way to just represent repeated addition. The indexing is what's kind of interesting with this. This is sometimes read as for I equals, oh, actually, this is already in the notes. This is usually read as the sum for I equals 1 to n of the xi values. And our author discusses some pseudocode around this. If you think in terms of for loops, if those are things you've programmed before, that's a great way to think about what's going here. So I'll leave you to the reading on that on the pseudocode. What we'll practice is just doing the evaluations on a couple quick examples, similar to what you're dealing with in the homework. So first one, we're evaluating a summation as the index I goes from 1 to 4 of the expression 2i. In order to do that, all we need to do is just expand the sum like we see over here. Think of xi as being the 2i, or x1 as being the 2 times 1 right here. So we'll get 2 times 1 plus, after we do that, well, the index was I equals 1 to get the first term of the sum. Then we increment the index by 1 integer, keep on incrementing until we get up to 4, where we end the process. So this will be for I equals 2. We have now 2 by 2. Then continue on, I equals 3, so plus 2 by 3. And then for I equals 4, we have plus 2 by 4. So altogether, this is then 2 plus 4 plus 6 plus 8. Looks like altogether then we've got a 20. So that's what's going on with our summation notation down here. The further reading that I didn't indicate you have to read right away in the book that you're free to skip through is dealing with nested summations, double summations, those kinds of things. Gets pretty fantastically tricky. But let's try out one more, just for the sake of practice. Any questions at all, folks, on how we got these expressions or these values out here? Oh, that was not continuing that way. Okay, for one last one, This one's a little bit odd since the index is starting at 0, but really there's no rules here. This could go from -25 to +16, anything like that, and you'd be just fine. So instead of writing these out, let's just go write them in as we see them. When I is 0, we have 2 times 0 minus 1. Parentheses here aren't really needed, but it's just a great way to organize. This is one term in the summation going into the next term. So same thing, except that part is just incrementing till it gets up to a 5. So we have a 2 by 1 minus 1 plus a 2 by 2 minus 1, 2 times 3 minus 1 plus 2 times 4 minus 1. Really hope to get that in one line, but always use this trick if you have to. Drop down a line. 2 by 5 minus 1. So the index going from 0 to 5 is conveyed here when we expanded out the sum. Now we need to calculate it. So let's see what we've got. It's a -1 plus 1 plus 3. Notice the pattern we're getting here. These are really just odds. And in fact, 2i is a way to express even numbers. Let's say integers, just to be explicit. And 2i minus 1 is a good way to express odd integers. So continuing on, we have -1, 1, 3. Here we have 5 plus 2 by 4 is 8 minus 1, 7, just making sure it's odd so we didn't make some weird mistake. And then 9. So summation on this one looks like it's going to be a 23. Let me know if my arithmetic went south on that. 10, 15 plus a 7. That doesn't sound right. It sounds like a 22. Oh, was that 24? 24. Thanks for the help on that one. Arithmetic is always the first thing to go in if you're tired, so I appreciate the support. So that's our result for that summation there. So nothing too major with the summations that we're looking at in this introductory section. We have to deal with more complicated nested summations, things like that. We'll devote extra class time to make sure we have that concept ready to go. I felt like doing it on the first day, first section of the book was a really rough time. Well, any last questions then, folks, on getting through any of these introductory topics? Okay, well, we did it, folks. That's our first section of the textbook. We're on our way through the course material. Let me save this up. And I'll get this uploaded to the Moodle website a little bit later after class, once this saves. Now, these computers used to feel modern, but they're starting to show their age at this point. Probably shouldn't have converted to the PDF. I forget how much class time that actually takes. Well, you know, it's a good mental break, so not the worst thing in the world. So for our next concepts, we're getting into the more heavy-duty feeling kind of topic, set theory. The set theory that we're discussing is sometimes called point set theory, or other times it might be called point set topology. So set theory is one of those things where it is really pervasive everywhere in mathematics. We'll see in the later section of this book, in fact, if you really want to define a mathematical function, it is defined in terms of sets in the very first place. That's kind of an interesting concept. So the major things we operate in mathematics, functions, are themselves sets. So it says here for our concept, a set is an unordered collection of objects. That's not really saying too much. So my goal here was just to provide us some ideas of what a set could be. So let's just call this maybe example 1, part A. Here's our first example we're going to provide. Oftentimes, sets are indicated with uppercase letters. Sometimes the first part of the alphabet, sometimes the latter part of the alphabet. Or if you know what the collection of objects are, sometimes we select them phonetically, like the author says. So for example, if we're dealing with, say, a set of numbers, it could just be something like this. Ordinary set of integers like we were discussing in the last section. So this is a set. If we want to try to enumerate it, it's impossible. It has infinitely many elements, but we can give a try by writing it down in this kind of way. go from -3, -2, -1, 0, goes to the left, conveying the obvious pattern that we see here, one integer being subtracted each time, then 1, 2, 3, and so on. So that would be a decent example of a set. Other sets could be just simply things like this. A equals 1, 2, 3. And it's a perfectly good set in its own right. Things that are interesting again is that a set is an unordered collection of objects. And so we can also say A is also equal to 3, 1, 2. The order you write down the elements in your set A is totally irrelevant. All that matters is what is inside the set. And the things inside the set are referred to as the elements of the set. Any questions so far, folks, with those examples we have at the moment? Sorry, say again. I would say objects would work just fine as well. Our author goes between things like elements of the set, the members of the set, or the object of the set. That's kind of a synonym in all those kinds of ways. So I would say if you went object of the set, that'd be kind of like a stylistic choice of how you're conveying your work. Other questions at the moment? Okay, well, here's another way to write out the set A. One thing that's kind of, I'd say, a little bit niched about these sets is that it's an unordered collection of objects, but we only care about the distinct objects. So if we write down a set A like this, 1, 1, 2, 2, 3, we've duplicated some of the elements or objects of the set. Well, this just could be reduced and simplified back down to 1, 2, 3. It is still the set A because a set is really only interested in the unique individuals that belong to it. So that's, again, something weird about these kinds of sets that we'll get used to as we go along. So far, we've looked at a couple interesting sets. We've dealt with sets of real numbers just in the very last section. You can't escape them. We were looking at interval notation, and then we expressed them as sets. But out of all the sets we've taken a look at, there's one which has a really, really interesting importance. It is the empty set. The empty set is, I often write it this way. So it looks like you're trying to indicate the number 0, but this actual circle slash is a way to say the empty set, or sometimes called the null set. Equally valid formation or equally valid notation for this is writing down the set symbol, a curly brace, kind of like what we are doing up here to indicate a set. If a set's meant to be empty, we just close it, and both the thing on the left, the thing on the right, fully synonymous. You can indicate your empty set like this if you prefer, or like this if you prefer. Truly a pretty weird set, and this is where sets get even stranger. We go to part D, we can say that this set is not empty. Let's write down the set. It is going to be the set that contains the empty set. Let me see if I can write that down better. So this set is not empty, even though the one member inside this set is an empty set. It means the larger set that's containing an element has something in it. It contains the null set. So as weird as this looks, that set is not empty whatsoever. For me, the reason I like the symbol on the left is I think this is actually kind of hard to look at. Sometimes it's easier to convey the set containing nothing but the empty set in this sort of way. So sets are a little bit weird, and there's lots of different ways to convey your sets like we saw in part B. And maybe for an even weirder example, the set B equals, I'm looking up here for my new weird example. B is going to set of sets. It's going to contain the set 1, the set 2, and the set 3. It almost feels like we're just making really huge issues out of small things notationally, but that's actually really, really important. In computer science, instead of saying sets, you might say something like lists. And you can create lists of lists. And in computer science, this list is not the same as this list down here. They have a totally different structure. So that set B is not the same as A equals 1, 2, 3. So those are our first early examples of sets that we're going to be looking at in this course. Any questions or comments before we get to the other related concepts with this? Okay, well, we have some examples of sets, but if you want some even bigger examples, you could go to the Moodle website. Let's take just a small break. And this is the optional reading for other kinds of sets that come up quite a bit, the more and more math that you take. This one is a little bit out there, but if you're interested in the subject of topology, not topography, topology, this is all about just dealing with sets. It is considered very optional, so if you open this document and you don't like it much, feel free to just close it and never look at it again. I'm going to leave that completely up to you to take a look at. I think the better example for us is vector spaces. If you're going to deal with a vector space, you must start with an empty set V of objects called vectors, and you automatically are going to begin dealing with non-empty subsets of the original set V. We would call those subspaces. So the entire subject of linear algebra is really all about this stuff. That's the domain of your linear functions that you would be dealing with, the vector spaces or subspaces. And just about everything in math, like we said before, in some way, shape, or form, ties back to sets. It's kind of interesting in a way. Set theory is also considered very modern mathematics. It was pioneered by a man called George Cantor. He was later deemed clinically insane because no one accepted his work, but his work was massive and fundamental. Later on, after his death, he was posthumously honored as a very premier mathematician because his work became just widely accepted and used almost universally. So here's where we're going to begin some notations, some machinery on combining sets, and all that great stuff. First, Ethan says, oh, gotcha, no worries. You'll be able to take a look at the video right after when you get a chance. But other questions so far? Okay, so here's our first big concept, set membership. We take a set of any objects which we call X. You might have seen this expression floating around in different math books. If we say X, that little symbol there, what we're saying is X is an element of S. So if this statement is true, then whatever X was, it had to have come from the original set S. So X in S is usually how we write that. A lot of times people just abbreviate that whole symbol as in, or you could say element of. So X is an element of a set X, is what you could say, or just X is simply in S. A lot of times in mathematics, this is a kind of a weird stylistic issue. We're really focusing on set theory, so we're going to use a lot of these special symbols. But in later math books, a lot of mathematicians just would prefer to say one is, let me say it this way, a lot of people would just say one is an A rather than using that special symbol. But this does have its place. If you want to write down things as compactly as possible, these are great symbols to work with. So we have a set A. It's going to be the set of all prime numbers. And the question is simply, is one an element of that set A? Well, that's an interesting set that we indicate right here. I can't write down this whole set, but there's a couple ways to indicate it. This has been indicated just completely with a ordinary English description. We could also say A is equal to 2 That's just the first prime number. 3, 5, 7, 11, and so on. So this is another way to convey the set. For looking at the question, is 1 an element of the set A? We would have to say no, 1 is not a prime nor composite, or another way to think about it is it's nowhere inside the set if we're looking at the actual written out expression here. So we can say no. 1, if you like symbols, you can now say 1 is not an element of A, since 1 is not prime. Well, any questions, folks, with that terminology here? Okay. How about the number 43? Anyone happen to know if that number there is prime or composite? You know, if you're not sure, sometimes you could do things like pull out a calculator, start dividing things, or you could just simply ask Google, is 43 prime? This is not going to work for very large numbers, but Google is pretty quick with something along those lines. 43 is a prime number. It's only divisible by 1 and 43. So you don't have to work too hard on these kinds of things, doing the test for all the divisions to test for primality. We can say 43 is prime. So yes, 43 is an element of the set A, is how we can convey that. Let me make sure I close this window. So that's what's going on with set membership. Other things we're going to take a look at is the size of the set, cardinality, how sets relate to each other, whether they're subsets and so on, proper subsets. But any questions at the moment? Okay, well, let's get into cardinality of sets. This starts to get pretty interesting mathematically because cardinality is sometimes something that's easy to calculate. It can also be something that is fantastically difficult to calculate, especially if you're discussing what is the cardinality of the set of real numbers, for example. That's actually a pretty tough question. Well, we say the cardinality of the set S is denoted in this way. Absolute value S is trying to say the size of that set S, and it's the number of the distinct elements in the set itself. So we could say the cardinality of the real numbers is infinite. There's infinitely many real numbers. We would express it in this way. Cardinality, the real number system is, let me fix my cardinality expression. There we go, just 1 bar is infinite because we have infinitely many elements. The cardinality of the set of all integers is also infinite. So that's kind of interesting in a certain sense, yet there's a little bit more going on here. The size of the set R is truly bigger than the size of the set Z in a very real sense. We need functions to make this more clear, even though we put infinity on both of these for their cardinality. But let's test this out on some more routine examples that we'd see in a class, or the homework rather. Here it says we want the cardinality of the set A. This is the set A up here. A volunteers for what the cardinality should be on this one. It's meant to be kind of a tricky example because of that 3, 2.
I'm going to guess 4.
Yeah, absolutely. Some folks in the class are also indicating 4, and good call. It's so easy to say 5, right? But we have to pay attention to this symbol right here by the red dot. The 4th element is a set, and that's just one element in of itself. Sure, the cardinality of 3, 2, we would say is 2, because that set itself has 2 elements inside of it. But this set has 1, 2, 3, and this whole thing right here, that's hard to highlight, this whole thing right here is the 4th element. Maybe we can convey it this way. That one is the 4th element in the way it's been listed in this situation. So the cardinality of that set A would be 4. And forgot I put this here in the notes. I kind of gave that away. This set is infinite, so whenever we're dealing with an infinite set, we would just write out cardinality is infinity. There is no finite number of distinct elements, so we just throw an infinity on that expression. So far we have ways to define sets. We have ways to tell if an element is in a set. We know the size of sets, so where this is all going next is a more interesting way to indicate sets. Our author calls this definition set abstraction. I think that's a really great way to convey this concept, because sometimes we list sets in this way, saying what all the members are. Occasionally we might write out sets like this, or in this kind of way, where we convey a pattern that must continue. But there's a totally new way to define sets as well. At the very end, there's a blurb in section 2.3 to indicate how this process of indicating sets really matches pretty closely in computer science on how some lists are really built using filter functions. So even though you don't have to read the end of these sections, I'd say the reading in section 2.3 at the very end, the computer science connections, are really pretty interesting as well. So give those a look if you're interested in. There always makes the material more readable and relatable if you can see those kind of connections. So first we start off with U, the set of all possible elements. We're going to call that the universe. That means any set we try to write down has to have elements that came from U if we have such a situation. So this is the collection of everything. If we're dealing with a number system, the universe could be all real numbers, or sometimes it just could be some finitely many elements we're considering. Now, P of X is either called a condition or a predicate. When we get more into logic in chapter 3, we will use those kind of verbiage more. What it does is it does a check. For each X you pick in U, you throw it into this condition, and it's either going to be true or false. We have an example down here we ought to take a look at. The X's here come from a universe, the real number system. So here R is playing the role of U. We have a condition or a predicate statement, P of X. In this set, that statement is here. Sometimes I call this a set membership condition because it's a condition that has to check as true in order to build the set. So this set S is going to be the collection of all X's such that some condition P of X, here's our condition, happens to be a true statement. And looks like I defined the empty set here in this situation. We defined it a little bit earlier at the top of the notes as well. So looking at this set S rather, this one turns out to be, anyone happen to see what it might be? Good call, this one is the null set. Reason being is this condition, x squared plus 1 equals 0, is false for every single real number because of this problem. X squared plus 1 equals 0 implies x squared equals -1. However, x squared is greater than or equal to 0 for all x in R. Later on, we're going to use even more symbols. Instead of saying for all, we can make that even more compact. But I think it's rude to introduce notation before it appears in the book, so I'll hold off on that kind of stuff. But here, don't forget that saying this means just element of, or it's a member of the set. So if this statement here is always false, we get the empty set for the set abstraction of that set S. There's just no elements that makes it true. Looking at part B, I think I have a typo right here. Our author has a way to write down subsets of real numbers by what should put here greater than 0. Let me put this in red to convey that quick edit. Sorry about that typo there. So let's write out what z greater than 0 would indicate. Z greater than 0 would be the set 1, 2, 3, and so on. So these are the natural numbers, sometimes called the counting numbers. We said greater than or equal to 0, we would just include 0 there and call it the non-negative integers instead. So this set has a universe, z greater than 0, so it's playing the role of all possible elements that we can throw into this set. our condition is that x squared plus x minus 6 has to be 0. But this just turns into a little bit of algebra, so that's kind of a fun algebraic review. This is a set B, but we can start writing out equality and say that this is all x in Z containing the positive integers such that in blue, we can do an operation on this. It's an ordinary algebraic expression inside the set. So anything you could do legally in algebra, we can do right here. Let's factor it and get x plus 3, x minus 3. Let me try again. X minus 2. That looks a little bit better. Equals 0. Sorry, a little rusty on factoring this evening. We would get a negative 6 here. Yeah, that looks like the right factorization. And that equation would have two solutions. We have from here, x would be equal to negative 3, or x would be equal to 2 when we're considering that equation. But not both of these are actually members of the set because they have to come from this universe. We're only allowing into this set the positive integers. So when we go to the next step, this set contains exactly one element, positive 2. Although the terminology isn't super important, sometimes the author does say this, so it's important to be familiar. This is a set with one element, and so it's referred to as a singleton set. Well, we did it, folks. This is expanding out a set by exhaustively listing its elements. It wasn't too exhaustive. There was only 2 possible elements, and we restricted to exactly 1. But exhaustively listing its elements is more targeted to this last set down here. Here we'll combine some modular arithmetic and build out the set H. H for, it's a harder example, I guess. But any questions at all, folks, before we go off to part C? Okay, so one more set to build. And really concerningly here, well, not as concerning, is that the universe is all integers. More concerning, in my opinion, is that we have an equation to solve dealing with modular arithmetic. But what we're going to do is follow our nose by exhaustively listing all elements. There really is a lot going on with modular arithmetic, but we don't have too much machinery at the moment to really show how to get into those kinds of things. But notice there is 2 conditions here. There's an and inside, then we also have a restriction that the integers n only go from 0 to 20. Both conditions have to hold simultaneously. So here's one way to build out this set. This one's pretty similar to a homework question, so that's why it's here definitely to support the homework. And when I try to do this on my own, it's easy to get kind of mixed up with this equation right here. I felt that this was a good format to give it a try. Write down a table going n. It is kind of tedious, sorry about that part. But I felt like if I assign something tedious, we ought to do at least one of them ourselves in the homework. Now, we have a column for an n. I want a column for the left side of the equation, n mod 11. Column for the right side of the equation, n mod 13. And we're going to allow n to vary from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, oh geez, 16. Let's put this on a new page. It looks like that's going to be required at this point. Okay, almost there. I think we can fit this on one screen at least. 17, 18, 19, and 20. Never seem to make these tables long enough. But actually, this table is not as bad as it seems to be. It's more tedious just to build it out, I'd say. I could have used the table structure inside Microsoft Word, but I felt like that's cheating. If anyone's doing this along with me, that'd just be a rude way to speed line through it. Oh boy. It's harder the longer you do it. That's the interesting thing about this.
Okay, that's the worst part of this whole problem. Now we can get started on column 1. We want equality right here between these two expressions, n mod 11 and mod 13. But using the concept from just the very last section, when n is 0, we're taking the remainder after division of 0 by 11. That remainder would just be a 0. If we do 1 mod 11, just like how we did, I believe it was like 5 mod 17, the value would be 1. In other words, 1 divided by 11, it goes in 0 times, a remainder 1. And this pattern keeps on going. In fact, once we get to 11, this is when it turns out to be a 0 again, and this turns into a cyclical process. This is where an algebraic structure emerges, groups of symmetry. So at 2, we get an output of 2, and so on. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 11 mod 11 resets, we get 0. 12 mod 11 gives us a 1, and this whole pattern just reconveys. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's double check. 11 goes into 20 once. Yeah, remainder 9. That sounds about right. Same exact process over here. The only difference is we'll go from 0 all the way down to 12, where we get 12. So this repeats from 0 up to 12, and then goes 0 up to 12 again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, it's a good reminder that author says exhaustively listing its elements. That's what we're doing here. This is the experience of doing something exhaustively. Kind of tedious, but once you get the hang of it, it's not so bad. So hang on, I think I made a mistake here. 13 mod 13 should be a 0, right? So it should have stopped right at a 0 on this one. And now we're repeating all the elements. So 1, 2, 3, 4, 5, 6, 7. So we wanted a set of all integers n, for which n mod 11, it was equal to n mod 13. And here's their outputs. All those integers n are going to be 0, 1, 2, 3, 4, 5, because all the outputs on the right are the same. 6, 7, 8, 9, 10. But when our column 1 resets to 0, we have mismatches all the way down. So we can say our set H is equal to 0, 1, 2. It did say exhaustively list out all elements, but you know what? If you use this little structure here, dot, 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 and give me a 10, you wouldn't be doing anything too different than the author does himself in writing these out. That is a decent shortcut to take in this situation, because everyone would read this as the most obvious pattern is continuing. It would have to be one integer added to the next. Well, we did it, folks. This is building sets abstractly from scratch based off a predicate condition that has to hold. We'll be doing lots of this kinds of stuff. It turns out this sort of work right here that we're dealing with can now be combined with other kinds of sets. We'll be dealing with things along the lines of, let's go down here, partitions. Partitions play a huge role in mathematics. They get rolled into something called equivalence classes, which is a way to extend the concept of equality, like 5 equals 5. We say everything in this set is equal to each other when it's part of a partition. And then an even more scary, fun concept is the power set of a set, the set of all of its subsets, every single one. This one is an interesting concept as well in its own right. This one's tied into probability theory in the oddest of way. Probability is a probability set function, which takes a set from a power set and assigns to it a number between 0 and 1, including the boundary values. So that's one weird connection to this idea already. But we're getting into the cusp of some of the set operations. So I feel like this is a good segue point for us to continue these notes on the next class. It'd be good to do these all as just one big unit. So we'll stop a little bit early today, about 5 minutes and some change. But any questions from the class at the moment before we call it a night? Okay, again, if you're interested in more and more things you can do with sets, take a look at these two examples here, but it's really just about everything. The bigger example we're going to see for the use of sets is when we get into the later section in this chapter, defining functions, which we've done plenty of times before, but now we're defining them in a more primitive way. We're using sets themselves to say exactly what a function really is. Well, have a great night, folks. When we come back on, oh, hang on, we have Martin Luther King Jr. holiday already. We've been working hard and we've already got a holiday. We'll come back a week away from today and continue on this assignment. Pretty much what happens on the Moodle website is everything is pretty dynamic. We're not going to finish this section today. So what I do next is I just move it over down to the next week in this kind of way. Where these things land on and stay is the week at which we finish the course content. So if it feels like things are moving around, that's the whole purpose. We'll be pointed right here when we come back a week away from today. But have a great weekend, folks. Have a great holiday. If you have any questions, don't hesitate to reach out by email. I check my email even on Martin Luther King Jr. holiday. I check it in the morning.